Welcome to Physics Chapter 19. This chapter is about electric current and resistance. But we have to review a few things from Chapter 18 first. The electric field strength is the amount of electric force per unit charge. Potential electric energy, or electric potential energy, is the energy difference due to the position of a particle within an electric field. And potential difference is the amount of electrical potential energy per unit charge. So we talked about protons, electrons, different particles with different charges, and how being in a different spot resulted in different amounts of potential. What does that have to do with current? Well, the difference in potential energy is what causes or maintains electric current. So we had to understand the force behind current before we can really understand what current is. You'll see here that current is represented by an I, a capital I. I'm not sure why, it just is. So what is current? Current is the rate, and I've underlined rate because it does have a time factor. It's the rate at which charged particles move through a given area. If we're talking about a wire, it's the cross section of a wire, which would be a circle. So the area is, if you remember from geometry, pi r squared. Current is measured in units called amperes, symbolized by a capital A. The formula is I equals delta Q over T, where delta Q is the amount of charge that passes through the given area. The units ampere, 1 ampere is equal to 1 coulomb per second. Note that anytime we have something that is a 1 over seconds or a per second, sometimes written as s to the negative 1, we actually call that hertz, which is symbolized by Hz. So a per second is hertz. The formula can be rearranged to solve for the charge, the time, and technically we can calculate the number of electrons that are flowing or the number of charged particles if we know their charge. Because delta Q, the charge, is equal to the number of the particles, so for example electrons, times the charge of that electron. So if we remember, the charge of an electron from chapter 17 was negative 1.6 times 10 to the negative 19 coulombs. With this formula, you can do the calculations in practice 19A on page 695. I will post those answers in a separate document so that you can check your work. And if any time during this video you need to pause to take notes, I mean, you have that ability, so I'm not pausing during the video much, just so that we can get through it in a decent amount of time. All right, so they had to throw something that is difficult in there. Current, for some reason, is defined conventionally as the direction of the flow of positive particles, or the apparent flow of positive particles. So current is defined as positive in the direction of the same direction if it's the positive particles that are moving. This is not very common. We only usually see this in examples such as particle accelerators. If it's a negative particle that is moving, the current is defined in the opposite direction, and this is actually what we will most usually see. It's very common anytime we have a solid conductor, solid metals, etc. And it's not that different from gravity, where convention says that up is positive, but gravity pulls down. So if you think of it like that, it's not actually that difficult. You just have to drill yourself to remember that when you're doing the problems. Negative signs, right? The third situation is there are some cases, such as ionized gases and electrolyte solutions, Remember, an electrolyte solution is anything, has any solution, liquid solution that has ions dissolved in it. If the positives can flow one direction and the negatives will flow the opposite direction, the convention is still defined in the positive motion, but you have to account for both the direction and amount of the positive flow and the negative direction and amount of the negative particles. So I've kind of copied page 696, table 19.1, just to show this. If the negatives are moving to the left, then the convention is that we define current to the right. If the positives are moving to the right, conventionally we define current moving to the right. And if we have positives moving to the right at the same time that negatives are moving to the left, by convention we sum the two directions to the right. When we think of electrolytes, you may have thought Powerade, Gatorade, Propel, electrolytes dissolved in water, salts, sugars, oh, not really sugars, salts or any other ions. Another thing that can cause some misconceptions, some confusion, a lot of people think erroneously that an electron moves at the speed of light. So when you flip on the light switch, the light bulb comes on immediately. So that they think that that electron has flown from the light switch to the light and back to the switch in an instant. But that is not the case. In reality, electrons actually move fairly slowly, even through the best conductors. When you flip the switch, what happens is the electrical potential difference is created. That creates then an electric field throughout the circuit, and that happens at nearly the speed of light. It causes electrons throughout the conductor to begin moving simultaneously. So electricity is not caused by one electron flowing from the switch through the appliance and back to the switch. It's caused because throughout the circuit, once that potential difference is created, the electric field goes throughout at the same time, and electrons all throughout start moving at the same time. So one electron near the switch starts to move at the same time another one a foot down the wire starts to move, and near the light bulb starts to move, and then after the light bulb starts to move, it takes billions, trillions, gazillions of electrons all moving at the same time for electricity to flow, for us to run our appliances. So I mentioned conductors. We know that conductors are substances that allow electrons or charged particles to move freely throughout. They allow those particles to move with very little restriction. The less restriction, the better the conductor is. Metal conductors, the reason, this goes into chemistry, so the reason they conduct so well is that they tend to have electrons that are shared. This is how they bond. For every nucleus, there are 1, 2, 3 electrons that are free to move around from atom to atom. I like to compare this to stray cats in the neighborhood. They're free to move. It doesn't matter where they started. They can go eat at this house and then that house and then this house, and it doesn't matter. They're shared throughout the neighborhood. The reason this happens, and this, please excuse my chemistry drawing here. We know that there's a positive nucleus, and I drew this way too big. We know it's a teeny tiny speck in the center of the atom, but just to show that there's a lot of positive in the middle, I drew it big. Copper, for example, has 29 electrons, and the inner electrons are held close to that nucleus. The positive attracts the negative, so the closer they are, the more attraction there is. This poor little guy out here on the very last energy level, he is held very loosely, kind of like out of sight, out of mind. He's not only is he the farthest away, so like all these other ones are blocking him from the nucleus, they also block the attraction. So the ones closest are the most attracted, then the next energy level, and so on and so forth. So by the time you get to this guy, he's pretty much free to roam around. So this is the electron. These outer electrons that are held loosely are the ones that can move around. So there's your chemistry for the day. So I drew a wire, and this electron that might start here can bounce from one atom to another, and notice that this is a very zigzag pattern. It's not all moving forward. It's not a straight line. That's another common misconception. These electrons can move by bouncing. Bounce, 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 bounce. Overall, the net velocity is in this direction. We call that drift velocity because it accounts for both the forward and the backward motion of those charged carriers. And an important note, we'll get into this later why this is so important, but as the electrons collide with the particles, anytime there's a collision, there's a little bit of motion. So the particle will actually move more. More motion, more velocity, equals more kinetic energy. Kinetic energy, if we take the average kinetic energy of all of the particles, that gives us the temperature. So if we're increasing the velocity, we are increasing the kinetic energy, and therefore these collisions mean an increase in temperature within the conductor itself. This is why when we have electricity running through wires, they actually heat up. So like I said, this is not just one electron moving, as I showed before here. This is one electron's path. There are electrons from all different atoms moving along that wire. Here I chose 10 or 12 different colors to show the paths of different electrons, and it's a jumbled mess. So if you can imagine this multiplied by, I don't know, 10 moles of electrons moving, you can see that it is a jumbled mess, but still overall they're moving in a net direction. I also wanted to show a little diagram of an electrolyte solution. So this is some liquid solution with some positives and negatives. This might be sodium and chlorine, or some other dissolved salt maybe. If we apply electric potential from one side to the other, the positives will flow towards the negative terminal and the negatives will flow towards the positive terminal. And this is the example showing that electric can happen when positives move one way and negatives move the other. So they're both moving at the same time. By convention, this showing electrons all moving to the right means that the current would be defined to be moving to the left. In the electrolyte solution, positives are moving to the left, negatives moving to the right. So therefore, again, the sum of both of those particle motions would end up having a current to the left. So we would have to apply a source for the current for that potential difference. Otherwise, the electrons are just going to stay hanging around in one general area. Those electrolyte solutions are just going to stay in equilibrium, evenly distributed. So where do we get current? You're all very familiar, especially with cell phones and devices. Batteries are sources of electric current. They use chemical reactions to create the potential difference between the terminals. We have the positive and negative sides. And that causes the charges to flow from one terminal to the other. And that creates what's called direct current. The power companies where we get our electricity from on the grid, and some people use these. We have a generator at our cabin. If the power goes out, a lot of people have backup generators. Generators convert mechanical energy, so that's energy of moving parts, to electrical energy. One example is hydroelectric. The water falls and causes a turbine to spin, and that can create the potential difference, which allows electricity to flow. So our outlets, this is my picture of an outlet, create potential difference between the two holes in the socket. So one would have a higher potential energy than the other. When you plug in your device, it makes a connection. So the electrons want to flow from the higher to the lower. Maybe I have that backwards. And then remember this little dot, that little extra plug at the bottom is grounding, and that is for an excess of electrons to be able to flow out instead of overloading the system. Generators can actually create direct current or alternating current. So what is direct versus alternating current? These are actually, I do know why they came up with these names. They make sense. Direct current is when charges move in only one direction. This also accounts for positives all moving one direction, negatives also moving the opposite direction. But the idea is they end up a distance from where they started. They follow a general path in one direction. This is kind of like everybody line up in the hallway, stay single file, walk down to the cafeteria, stay in line. So it's a single file line, but all of those electrons are moving in that line together in the same general direction. Whereas alternating current happens when the motion of the particles actually changes, because there's a constant switching back and forth between the terminals. So a potential here is higher and here is lower, and then they switch. So this one is lower and this one is higher, and then they switch back and switch back. And when they switch, the electrons basically vibrate back and forth. They go one direction, then the switch happens, they go the other. So they keep flowing back and forth from positive to positive, positive, positive. And then what you end up with is the electrons stay within a fairly small range of where they started. This is kind of like crazy running amok in a circle. You don't get very far even though you're moving a lot. And again, a whole lot of electrons are doing this at the same time. Alternations actually can cause disruption when they switch back and forth, but because it happens so quickly, we don't notice. In the United States, our electric grid works on a 60 hertz system, so that is 60 switches per second. If it was much slower, we would actually notice the lights flicker every time it switched back and forth with with alternating current. There are pros and cons for each type of current. There was actually, we could spend weeks talking about Westinghouse and Edison both wanted their type of electricity to be what was supplied the nation, but Westinghouse won with the alternating current. And if you're interested in that, I'm sure you can Google it and find more information, but like I said, we could debate that and have a week-long discussion on it. There are pros and cons for each type, but here in the United States, in our grid, we use alternating, and a lot of our portable devices we use direct because we're using batteries. On page 699, there's section review. Number 2 is a calculation. 1, 3, 4, and 5 are more theoretical. You don't have to write those answers down, but at least give them a good thought. And then again, I will post those answers on a separate document for you to check your work. Check back in the next couple days so we can go over section 2, resistance.